welcome to the Deep Dive. So, you're here, you're curious, and today, honestly, we're going to shake things up a bit. We're looking at where life could exist beyond Earth. For ages, right, the big idea was always the Goldilocks zone, not too hot, not too cold, just right for liquid water on the surface, all thanks to sunlight. Or maybe, just maybe, some heat from volcanoes deep down. But what if? What if that's not the whole story? Our mission in this deep dive, to get into a really fascinating, maybe even game-changing study. It challenges those assumptions, pushing the idea of habitable into places we thought were just freezing dark dead zones.
Exactly. And it's pretty surprising stuff. This research points towards an energy source for life that, well, it might be coming from somewhere we always thought was hostile. Something we never really considered as fuel.
Okay, yeah, let's unpack this then. Because it sounds like we're talking about cosmic rays, these high-energy things from space, maybe being the key, powering life hidden away beneath the surface of planets.
That's the core idea.
So for the longest time, astrobiology, it had these sort of rules, didn't it? Life needs sunlight for photosynthesis.
Or needs geothermal heat, warmth from inside a planet for chemosynthesis. It always boiled down to light or internal heat.
Makes sense, looking at Earth.
It's a very logical place to start, absolutely. But this new work, led by Dimitra Atri and her team at NYU Abu Dhabi's Center for Astrophysics and Space Science, KC-CERES, it brings in something really different. The idea is that cosmic rays, these high-energy particles, could directly power microbial life thriving under thick ice, under rock.
Hold on. Cosmic rays. I always thought of them as bad news, like radiation that sterilizes things. How do they flip to become an energy source?
Right, that's the counterintuitive part. It works through a process called radiolysis of water. So picture these cosmic rays like tiny bullets traveling near light speed, hitting water or ice deep underground. They don't just pass through. They have enough energy to actually smash the water molecules, the H2Os, apart. And when they do that, they create reactive chemicals. And crucially, they knock electrons loose. Free electrons.
Okay, so it's like using pure energy to split water, not heat.
Precisely. And the stuff left behind. Things like hydrogen gas, hydrogen peroxide.
Yeah.
Well, those are exactly the kinds of chemicals certain microbes on Earth already know how to eat for energy.
Wow. So organisms could literally live off these free electrons or the chemicals made by the cosmic rays. Kind of like how plants use sunlight.
In principle, yes. The energy capture mechanism is different, chemical instead of light, but it's tapping an external energy source.
And we actually see things like that on Earth. You mentioned microbes.
Oh, definitely. We have life forms, extremophiles, deep in the Earth's crust, totally cut off from sunlight. They use chemosynthesis, often munching on hydrogen or similar compounds produced by geochemical reactions. This study is basically saying, well, radiolysis could provide that same kind of chemical food source, the hydrogen, the oxidants on other worlds.
So places like Mars, with ice under the surface.
Exactly. Mars has a thin atmosphere, so cosmic rays get through pretty well, and there's lots of subsurface ice.
Or the icy moons, like Europa and Enceladus.
Perfect examples. They have these vast oceans under incredibly thick ice shells. The cosmic rays might not get all the way to the ocean everywhere, but they penetrate the ice, creating these chemicals within the ice itself or maybe near the top of the ocean. It's a constant supply of potential food.
Okay, so the team didn't just theorize this, they actually crunched the numbers.
They did. They used complex computer models. They wanted to figure out, okay, how much energy, how much chemical fuel could this radiolysis process actually generate on different worlds?
And this is where it gets really interesting, you said, because the results were unexpected.
Very unexpected, yeah. When they modeled it, everyone's favorite candidate, Mars, it came in second.
So what was first?
Enceladus, Saturn's little icy moon, the one with the geysers.
Enceladus, wow. Then Mars, then Europa.
That was the ranking in terms of potential energy production from this specific process, yes.
That is genuinely surprising. Why Enceladus? What makes it better for this than Mars, which seems, more obvious?
It's a mix of things. Mars gets a good dose of cosmic rays because of its thin atmosphere, sure. But Enceladus, it has that enormous global ocean under its ice shell, just a huge reservoir of water.
Okay.
Plus, its location within Saturn's magnetic field means it gets bathed in a specific kind of cosmic ray flux. And the model showed that the sheer volume of water available for radiolysis in that deep ocean could produce a really significant amount of these chemical fuels. More, potentially, than Mars in certain scenarios they modeled. Europa's similar, big ocean, thick ice, also a strong contender. But based on their calculations, Enceladus just edged it out for potential radiolytic energy yield.
So, okay, based on these surprising results, the study is suggesting a whole new idea, this radiolytic habitable zone.
Correct. Forget surface temperature and distance from the star for a moment. This zone is defined differently. It's about areas deep underground where water or ice gets hit by enough cosmic rays to reliably produce enough chemical energy to potentially sustain microbial life.
So the Goldilocks zone was all about surface liquid water. Location, location, location relative to the star.
Pretty much, yeah.
But this radiolytic zone, it's saying maybe life doesn't care about the star that much. It could be powered from the outside by cosmic rays deep inside a planet or moon. It opens up, well, huge possibilities. Entirely different kinds of environments.
It really does. It fundamentally challenges that bias we've had in astrobiology, the focus on sunlight or internal heat. If cosmic rays can genuinely create a stable energy source deep underground, it forces us to rethink, well, everything. Where life could be, it suggests life might be way more adaptable, maybe more common than we thought.
And the knock-on effects for space missions, they must be huge.
Absolutely massive.
Like for Mars, for decades, we've been sniffing around the surface, looking for old water signs, organic molecules.
Right, hunting for surface or near-surface biosignatures.
But if this is right, we should be looking for something else, like the evidence of this radiolysis happening deeper down.
Exactly. We should maybe prioritize instruments that can detect the byproducts, that hydrogen peroxide, the molecular hydrogen, deep below the surface. Not just centimeters, but meters, maybe tens of meters.
Which means we need better drills, different kinds of sensors entirely.
It points that way, yes. We're not just looking for water or organics anymore. We're hunting the chemical fingerprints of this specific energy reaction. We need ways to get deep samples and analyze them for things like, say, unusual hydrogen isotope ratios that might hint at biological activity consuming the radiolytic products.
And it's not just Mars, is it? You mentioned Europa and Enceladus being top candidates for the energy production.
For sure. This makes the case for sending landers, or even better, cryobots or penetrators, to those moons even stronger.
Things that can actually get through the ice?
Things that can get through the ice, yes. Maybe reach that ocean interface, or even sample within the ice shell itself, where this process might be most active. Potentially even sample near the rocky core if possible. We need to get below the surface radiation crust.
It's like finding out there's this whole hidden power grid for life we never knew existed. A dark, cosmic ray-powered grid.
That's a great way to put it. It opens up the possibility, a very real one, that we could find entire ecosystems thriving in these deep, dark places, completely independent of sunlight, maybe even independent of hydrothermal vents, just powered by energy raining down from the cosmos.
It just completely reframes what a habitable world could even look like. So this deep dive, it's really opened my eyes. We've moved beyond just thinking about surfaces warmed by suns. We're now considering these deep hidden places energized by cosmic rays. It's a radical shift for the search for life.
And it really leaves us with a pretty profound question, doesn't it? If these models are even partly right, if life can leverage this energy source in these unexpected environments, well, what truly amazing discoveries might be waiting for us, especially as we plan missions to Mars, Europa, and Enceladus. We could be peering into places that might actually harbor life, places we previously wrote off as completely hostile.
It really does make you stop and think, what does habitable truly mean? And what other secrets, what other potential homes for life are still out there, hidden right under our noses in our own solar system, lost to ponder?